Hello, MAT215 students. We've got several people in quarantine now, so I'm going to record this last lecture. It's actually our last content lecture. I'll post this on YouTube for you guys. So these inquiry problems from 4.4 we did in class, so I'm going to jump into the next part. We're talking about probability now, and we're going to define exactly what that is. And here they give you that definition using proper set notation, but really what it comes down to is the numerator, the absolute value of A. A is the subset, which is what the list of all the things you want. And so how many ways can you get what you want? And then U is like that universe, going back to chapter 2. That's everything that can happen, and how many things can happen is the size of that set. So they call that the sample space on the bottom, and the top is called an event, but it's really how many ways can you get the event, the thing you want, and then how many things are possible in the sample space, and you divide. Here's an example. They're going back to when we did Illinois license plates in 4.3 and how many different things were possible. They're not doing that again. They're referencing the previous section, and we got that number to be 24,336,000. So now here they're saying, how many ways can you get a plate that has the word Cub or the word Sox, because maybe you live in Chicago and you're a baseball fan. So that is going to be 10 to the third for Cub and 10 to the third for Sox. Now, if I remember right, these were 3 letters and 3 digits, and so the 3 letters are locked in, right? C-U-B or S-O-X, but then the other numbers can be any of 0 through 10. So that's where you're getting 10 to the third for each one. And then because those are disjoint events, you add it, and then you get that numerator, which then they did some simplification to get that last number. So very, very small chance of happening. Okay, here's an example if you've ever played Settlers of Catan, or another game where you roll 2 standard 6-sided dice. So what's the probability that you rolled 8, which means the 2 dice add to 8. So kind of like the heads and tails problem, you have 2 dice. There are 36 possibilities because one die can have 1 through 6. The other die can have 1 through 6. You multiply that because the dice affect each other, right? They add the sum. It's not 2 completely separate events. It's not that you can get one or the other, right? You can get all these different pairs. So there's 36 things in the sample space, and then they list, hey, here are the ways that you can add to 8. 2, 6, or 6, 2, we're counting both. 3, 5, or 5, 3, or then 4, 4. So there's 5 different ways to roll an 8, and so the probability is almost 14%. Actually, 7 is the most common, so if you've played Catan, the robber's on the 7, and that if you ever get sick of the robber, that's actually the most likely thing to happen. Okay, another trick with probability is that you can sometimes just take the probability of what you don't want to happen and then subtract that from 1, because 1 there represents 100%, which is, completely, definitely going to happen. That's all the probabilities are always going to add up to 100%. So if you roll 2 standard 6-sided dice, what's the probability you roll 10 or less? So rolling a 10 would be disjoint. Here you would add, it would be rolling a 10 versus rolling a 9 versus rolling a 8 and so on, and you would add all those up. Or it's much easier to just consider how many ways are there to roll an 11 or a 12, because there's only 2 cases now. Take those away. So there's 2 ways to roll an 11, which would be a 5, 6 or a 6, 5. And the only way you roll 12 is 6, 6. So those 2, there's 3 ways to roll those, 11 or 12. And so the probability of rolling more than 10 is 3 over 36. 1 over 12. So the 10 or less, you take away the 1 over 12, you get 11 over 12. You can also use this, by the way, in counting. There was a problem about, in your 4.3 homework, there was a problem about how many committees with at least 2 men on it. And what I did was I just took all the answers and I took away the committees with no men or 1 man. Okay, here's another application. So this is going to go back. We're going to go back to all those different ways to count. So here we're going to go back to decision trees. Starting at A, what is the probability that you pass the restaurant R on the way directly to point B? So the arrangements of how many easts and souths to go, we did that before. We'll reference that here, but it's it's maybe a little bit unclear about which way you can hit R. You can maybe do that with combinations, but here they use a decision tree. So here's all the different ways I can go southeast, southeast, and whatnot. And then out of the 6 kind of final bullets, 2 kind of the 2 main branches that both have 2 below, so 4 total, 4 different paths past the restaurant. So it's 2 out of 3. Okay, so here's an example of quality control. After I talk through this one, I'll give you a real-life example of what's going on here. So suppose there are 10 defective machines in a group of 200. A quality control inspector takes a sample of 3 machines and tests them for defects. How likely is it that he discovers a defective machine? So often with quality control, they don't check everything. They take a random sample and then they check those. So the sample space is how many groups of 3 machines he can pick, right? So that's 200 choose 3, and that's the denominator. He could get 1 defective machine, or he could get 2 defective machines, or he could get 3 defective machines out of his sample. That's 3 things to add, but it's easier just to take away how many ways can he not even detect the defective machines. How many ways could he actually get none of the defective machines? Out of the 190 good ones, he'd have to pick all 3 from that. So that's 190 choose 3. So that expression here, C193 over C203, that's, hey, we got away with it and no defective machines were caught. So picking a defective machine is take that away from 1%. So there is a 14 1/3% chance that he doesn't detect the defective machines at all. Now, an example of this quality control, I remember using this last year, a year ago, 1 or 2 years ago, before COVID, Marion's movie theater was shut down because they had bed bugs in several of their theaters. When the inspector came and did that, there's 12 theaters, and he only checked 2 or 3 of them, and he managed to get one. So there was a chance that he could have not noticed. He could have checked all the wrong theaters and not caught that. An example right now with COVID is random testing. So some people propose that, hey, you should just randomly test students, and 15% chance is probably too good of a chance to not catch it. So you have to scale the amount of quality control testing that you do, whatever the scenario is, so you get that probability as low as you're comfortable with. Okay, so another recent thing would be about voting and taking samples of voters in polls, basically. Rodelia wants to know if a majority of the voters in his town will support his candidacy for mayor. Suppose, for the sake of this discussion, that out of the 300 voters in this town, 151 support Rodelio, but Rodelio doesn't know this information. He selects 20 voters at random from the population of 300. What is the probability that out of this random sample, fewer than 5 support Rodelio? So what is the probability that he gets basically a sample that's pretty bad? Out of the 20, he doesn't even get 5 people who support him. Now here we've got to add this up. There's a lot of pluses here because fewer than 5 out of 20, well, you could have exactly 0 supporters or 1 or 2 or 3 or 4. And we could do the whole subtraction thing, but the other case is worse because it's 5 plus 6 plus 7 plus 8 plus 9 all the way up to 20. So the event, the numerator is, hey, out of the 149 people that don't support him, you can pick all 20. So that first term is I picked 20 people who don't like him. The second term, that product, is I picked 1 person that likes him out of the 151, and then 19 that don't, and then 2 and 18, 3 and 17, 4 and 16. So 0, 1, 2, 3, 4 supporters. So you have to add all that up, but that's all going to be on top of, you're going to divide that by how many ways can you just pick 20 people out of 300. That's 300 choose 20. And then we end up with less than 0.5%. So it's very unlikely that he'll pick a sample that has this little support. Which makes sense since over half the people support him. Okay, now suppose that Rodelia conducts a sample of 20 voters and finds that only 4 supporters support his candidacy. Do you like his chances to win the election? So what if this actually happens? The point they're trying to make here is really about the polls can have error, right? And so this is kind of going on right now, where some polls were pretty good for this election, and some polls, like in Wisconsin, were pretty bad. And there's a lot more context to go into that than just what we're doing here. But here, what should Rodell do in this case? Well, probably he shouldn't just do only one poll, right? There also might be some context. Maybe the 20 people he got are from a certain part of town, or their occupations are ones he's trying to eliminate, right? So with that small voter size, you could actually look for some context for, why was my polling so low? Of course, you can do that in aggregate too with bigger models. It's just a bit more work. All right, so the last thing is expected value. And so expected value is basically like the average expected value, what it sounds like. If you have a bunch of possible values that can come out of a situation, don't worry about them calling it a random variable, but basically you have the probability of something happening, and everything that could happen has a output that's a value, a number. Then you take each possible number that can come out times the probability that they happen and add it up. So this long sum at the bottom is really just possible outcome times the probability plus another possible outcome times its probability, and each outcome is a number, a quantity. That's the simple version. Okay, so here's an example with lotteries. So this is in the both ways version of Australia's Cash 3 lottery. You pick a 3-digit number from 000 to 999. And a randomly chosen winning 3-digit number is announced every evening at 5:55 p.m. If you pick a number with 3 distinct digits, you win 580 if your number matches the winning number exactly. And you win 80 if the digits of your number match the digits of the winning number, but in a different order. What is the expected value of the money that you win? Now, this is not considering the cost of the ticket, by the way. This is going to look like, hey, you can win some money on average. You got to keep in mind the price of the ticket. Okay, so the possible values that you can win, so the possible outcomes, possible values, are 0, 580, and 80. You can win nothing, you can win 580, you can win $80. There's 1,000 possible winning numbers because it's 000 to 999. Only one matches your number exactly, and 5 have the same digits. Why is that? Well, how many ways can you reach 3 numbers? That's 3 factorial, that'd be 6, but the winning number, that's in a separate pot, right? So we want to take away the perfect match. So out of the 3 factorial, which is 6 different ways you can rearrange those numbers, one rearrangement we've already excluded because it's part of the 580 situation. So in a different order. Okay, so how many ways can you win 0? Well, 994 of the 1,000 numbers can win you 0 money, so that's where that fraction is coming from. The 580, that's only a 1 in 1,000 shot. The $80, that's a 5 in 1,000 shot. So overall, you're on average, if you play this game a million times. Now, on average, you have to play lots and lots and lots of times, right? You play once, one of those 3 things will happen. You're probably going to make no. You're probably not going to win. But if you play lots and lots and lots of times, and then you average across thousands of plays, on average, you're going to get 98 cents. So the question is, how much would you pay to play? So the idea is, hey, if the lottery charges $1 per ticket, and on average people are winning 98 cents, the lottery is making money, right? But to you, you're like, oh, it only costs $1, and I could win $580. This is how gambling starts. So take this as a caution. If I had phrased this problem as, hey, what's the expected cost to you if the ticket costs $1? And I had incorporated that into the problem, the answer would be expected value is every time you play, you lose 2 cents. Even keeping in mind the probabilities of winning, which hopefully indicates that there's no point to playing, right? Because on average, you're losing money. Don't play the lottery is my bottom line there. All right, that's the last part of 4.4, so that's the final section. I hope this helps. I will be on Slack. If you need me, I can also Zoom. And if you haven't yet figured out, if I haven't talked to you yet about doing your last quizzes and exams virtually, just let me know.